All right, we're about to start, well, it looks like it says Unit 8, but it really isn't Unit 8. It's really Unit 6 for us. We're about to start simple harmonic motion. So Unit 6, if we do this, Unit 6 is simple harmonic motion. What we're going to be looking at primarily is we're going to look first at pendulums, and then we're going to look at springs. Those are the two primary things that deal with simple harmonic motion. So let's look at pendulums first. What is a pendulum? Well, most of you already know that. You've got a mass on the end of a string. Okay, we consider the string to be massless, and this thing is going to go backwards and forwards, or side to side, either one you want to think about, okay? Now what we know is that a pendulum approximates simple harmonic motion. It just approximates it. It's not exactly what we consider simple harmonic motion, but if we keep the angle of the amplitude, if we keep that angle right here, that it's going back and forth small enough, then, which we say is about less than 20 degrees or so, then what we know is it does approximate simple harmonic motion pretty well, okay? So the restoring force of a pendulum is the component of the weight tangent to the arc of the object's motion. Okay, so what do we mean by that? The restoring force, what is the part that wants to bring it back, is always going to be tangent to the arc. So the part that's going to restore is going to be going this way. So it's going to be the force restoring. Think about it. If you picture in your head, pulling a mass back on a string. If you let go, what's it want to do? Well, it wants to go back to where it was, doesn't it? So there's your restoring force, okay? So let's look at all of the various phases, we can call it phases, of a pendulum swing. So the first thing we know is the pendulum's going to start out here. So this is at t equals 0. We'll call this t sub 1. We're at 0. Okay? At 0, what do we know? We know that it is at its maximum value. So we are holding it out here. So it is as far out as it's going to go. And this is some position x. So x of t is at a max to the right. We also know that the velocity, we're holding it there, and we're getting ready to leave it. The velocity is going to be 0. The velocity at t1, excuse me, let me do this right so it looks better. The velocity at t sub 1 is going to be equal to 0. Now, what we know is it's about to go from nowhere down, okay? Now, the acceleration is going to be at a max, but it is going to be a max to the left. It has to be if this thing is going to not move downward. Kinetic energy and velocity are going to be connected, aren't they? They relate, don't they? 1/2 mv squared, so if the velocity is at 0, then the kinetic energy is also at 0. Potential energy has to do with how far it's pulled back. Think about it that way. Remember, potential energy is going to be, for a spring, is 1/2 kx squared. So the potential energy is connected to the x value. So this is going to be at a maximum, because if it's pulled back, if x is at a maximum, then the potential energy, spring potential energy, is also at a maximum. All right, so now let's look at t sub 2. T sub 2, let's consider this. There are 4 phases here until it gets back to itself. So if we consider this it starts, goes down, goes up, comes back down again, and then goes back up again, then we know it's one cycle. We call that the period. This is the total time t, which would be equal to the period. Okay, so this is going to be a quarter of that time. Think about it, it's 4 phases. Phase 1 is going from here to here. Phase 2 goes from here to here. Phase 3, and then phase 4. So you can see we've got 4 phases from start to bottom, to top to bottom, back to start again. That's 4. Down, up is 2. Down again is 3, and up again is 4. So we have 4 phases of this. So this is t over 4. That means t sub 3 is going to be at the halfway point. T sub 4 is going to be at the 3/4, and T sub 5 is going to be the full period T. Okay? So now, at the bottom, what do we know? At the bottom, it is not being tugged left or right. So at the bottom, the X is, if we let it settle, it would finally eventually settle at the bottom here, wouldn't it? If you were swinging back and forth, imagine it swinging back and forth with your head. It's getting smaller and smaller and smaller until eventually it's just going to hang. So we know that this X value is equilibrium. So this is at equilibrium. The velocity here, believe it or not, at the bottom, this thing wants to keep on going to the left. As a matter of fact, it's gained as much speed as it's going to gain, hasn't it? Think about this thing. It's going its fastest right here. So this velocity at V at T sub 2 is going to be at a max, only it's going to be at max to the left because it wants to go left. So this thing has swung down, it's going this way, and it still wants to go that way. So it is at a max. If it is at a maximum, then it wants to, it's going faster and faster and faster. Now think about what it's going to be doing. Once it passes equilibrium, it's going to begin to slow down, isn't it? So it's going to begin to slow down, which means if it's going at a maximum, but then it starts to slow down, what's happening to the acceleration? At the point where V is at a maximum, the acceleration is at 0. So at equilibrium, the acceleration is at 0. Now, let's get to our kinetic energy. Kinetic energy is connected to velocity. So if the velocity is at a maximum, the kinetic energy is also at a maximum. If this thing is at equilibrium, which is our 0 point, isn't it? Then the potential energy is also 0. And I want you to notice something. Notice what we're seeing here. We're seeing that whatever this is right here is the same as what's going to be right here, isn't it? Turns out, okay? And whatever this is, it's this and this. So we know these are the same. So we're going to see that relationship continue to develop. All right, so at T over 2, we're now up to the top here, which means it has stopped moving. So we know the velocity is 0. We know this thing is at X max, but this time it's gone as far as it can to the left, hasn't it? Well, if this is at a max, then we know the acceleration must be at a max. And it matches what? To slow this thing down to a stop. Think about it. If this were to the right, then the acceleration were to the left to slow it down and stop it. So if this thing is coming to a stop to the left, then the acceleration must be to the, to the right. Okay? So this is max to the right. And we know the potential energy also must be a max. Okay? Now, at T at 4, we're at 0 again. We're at equilibrium again, which means, so we're at equilib, which means the velocity must be, the velocity at T of 3 must again be a max, but this time, this thing is headed which way? It's headed to the right. So it is now a max to the right, which means this must also be at a max, correct? Because they have to match. Well, if this thing is at equilibrium, that means it is switching directions. The velocity is or the acceleration is switching directions, right? So it is 0. The velocity is switching directions, so it's 0, which means that our spring potential energy is also 0. I bet you can predict, looking at from line to line to line, if we're at T sub 5 now, we're back to the beginning of the cycle again. So shouldn't T sub 5 match T sub 1? We're going to be at X max to the right, which means this is going to be, our acceleration is going to be max to the, left. This thing is not going to be moving because it's going to come to a stop. And that means kinetic energy is 0. And if this thing is acceleration is a maximum and it is at a maximum displacement, then it must be at a maximum spring potential energy. So it is at a max here also. All right. Hopefully that all made sense. Oh, we left one out. This is also 0. Sorry about that, guys. So you should know and be able to think about how all of this relates. Okay? So at the upper ends, just to draw some parallels here, at the upper ends, here and here and here, notice what's happening here. These lines all pretty well look very similar, except direction is changing. At equilibrium here and here, those lines look the same except for what? Yeah, the directions, okay? All right. The velocity, which direction it's going to. Okay, so now let's talk about the period of a pendulum. The period of a pendulum is dependent on a couple of things. It is dependent on the length of the string, okay? And it's also dependent on acceleration due to gravity at its location, okay? Oops, gravity. Okay, more gravity. Let's see what happens. The formula is big T for period. So period is big T. It is equal to 2 pi times the square root of the length divided by gravity. So gravity is going to have an inverse relationship. The higher gravity is, the faster the period, the lower, excuse me. If gravity is higher, the period is lower. Think about that. It's going to be pulling it back down faster, isn't it? So that shortens the period. The longer the string is, the higher. So as L goes up, the period goes up. But as G goes up, the period goes down, gets shorter. And it does make sense if you think about it. That period is time, so the units is seconds. Okay, cool. All right, so you've watched this. Don't forget, know what this means. Be prepared to look at an example of a pendulum next time and be able to describe to me, talk with in relation to this chart that you're seeing right here, what the acceleration and the velocity is doing, which direction it's going, why we divide it into 4 chunks, etc. Let me know. So let's move on and look at some examples. Acceleration due to gravity on the moon is 1/6 that of the Earth, okay? The period of the pendulum of the moon is measured to be 7.6 seconds. By the way, we probably ought to... All right. So we know gravity on the moon is equal to 1/6 gravity on Earth. Okay. Period on the moon is equal to 7.6 seconds. Okay. So let's find the length of the pendulum because we know this. We know that period is equal to 2 pi square root of L over G. So period for the moon, that has to be equal to 2 pi times the length. It's not going to change on the moon versus Earth, but the gravity will, gravity of the moon. Okay, so let's plug in. This is 2 pi square root of L over 1/6 the gravity of Earth. So this is 2 pi times what? Length over 1/6 of gravity on Earth is 10. about thereabouts, and we're going to set that equal to 7.6 and solve. So what we end up with is we can do the math here. We can divide 7.6, divide both sides by 2 pi. It goes away. Now we need to square both sides, so that goes away. And then we're going to have to multiply by 10 over 6, which would be same as multiplying by 6 over 10. Dividing by 10 over 6, 6 over 10. What we end up with is approximately a length of 2.44 meters, okay? So if we know that, now we can use that to find the period on Earth. So the period here for Earth is equal to 2 pi times the square root of that length, 2.44, divided by gravity on Earth, which is 10. Work that guy out right there, and we get about 3.1 seconds. So we used the formula to find the missing piece, and then we plugged back in. All right, so let's talk about example B. We've got a 0.5 kilogram mass, 40 centimeter string. So what we know is that this 40 centimeter string tells us that the length of our pendulum is 0.4 meters, right? Okay. Mass is displaced at an angle of 15 degrees from vertical. Then it says calculate the frequency of the pendulum. So first thing we need is frequency. Frequency, guys, is just equal to 1 over the period. So that means we just have to turn everything upside down. 1 over 2 pi. And instead of L over G, it would be G over L. So now all we have to do is plug all this in. So 1 over 2 pi, square root of G, G on Earth is 10, and the length is 0.4. So there was a lot of unnecessary information in the first part that we didn't need for this, did we? So what do we find out? Frequency is 0.80. Well, if period is seconds, then, and this is the reciprocal of that, this would be 1 over seconds, or seconds to the negative 1, which would be the same as saying 0.8 hertz. Seconds to the negative 1 are hertz. All right, so now, let's see if we can find the next piece of the pie here. This is calculate the height of the pendulum, okay, above the equilibrium position. All right, so what we know is in equilibrium, it's hanging here. And what we've got is now got it hanging here. And we know this is 15 degrees, don't we? Okay, so that is 15 degrees. So what we notice is we've got a right triangle. We want to know the height of the pendulum above the equilibrium position. Here's a right triangle. This is L, okay? Which means we can find this chunk of it. We don't know. This is our height. Well, this actually right here is H. So let's call this what it is. Let's say we don't know. Let's say this is some Y value. Well, we can use trig inside this triangle right here. So here's our triangle. So if we look at this from that standpoint, what do we know? We're looking for adjacent, so this would be adjacent. We know this is hypotenuse, don't we? Adjacent hypotenuse is going to be cosine. So this cosine of 15 degrees is equal to that value y over L. So let's see if we can find what y is. Now, here's the cool part. I'm actually going to do this and make you do it with theta instead. Let's work through this because it's the same basic formula every time. Cosine of theta is y over L. So let's cross multiply and we get y equals L cosine theta. Well, if we want h, just this little chunk right here, we know what this entire length is, don't we? This entire length is L. So if we take L, h is simply going to be all of L minus y, which means it is going to be L minus L cosine theta. We've seen that before. So that would be our height right there. Okay? So let's plug in and figure out what it is. L is the length of our pendulum, and we said the length was 0.4, so this is going to be 0.4 minus 0.4 times the cosine of 15 degrees. If you work that out, then you get it's 0.014 meters. Okay? Now it says also draw a free body diagram of the mass at this position. So let's draw a free body diagram of our mass. What do we notice is happening here with our mass? What forces do we have? We have the weight due to gravity, and we have tension, don't we? That's it. That's really all we have is tension and this, which is going to be mg. Okay? Now, draw a free body diagram of the mass at its equilibrium position. So at equilibrium, it's hanging straight down, which means that we've got the weight down, and then the tension is straight up. Okay? So the tension is straight upwards, which means that we know those two things have to be what? Don't say they're equal. They're not, because this thing is moving in a circle. So with all of these, we have to consider that it is circular motion, which means the sum of forces, which is equal to m a centripetal. Remember, if it's moving in a circular pattern, you have centripetal force, which is towards the center. That which would be mv squared over r, wouldn't it? Well, that mv squared over r has to be equal to t minus the weight. Okay? Well, let's do this. Let's bring it up here. mv squared over r, and that r is actually L, isn't it? So this is really L, and we know this is T minus gravity, which is straight down, which is straight up mg. So if we want to solve for T, we simply add mg to both sides, which means we get the tension is equal to mv squared over L plus mg. Well, let's see if we can solve this and find out. So m is what? The mass is, I forgot, it's been so long, 0.5. The mass is 0.5, so 0.5. The velocity is, we don't know the velocity. How are we going to find the velocity, guys? Energy, that's how we're going to find the velocity. So to find the velocity, at equilibrium, we know it started up, so we had potential energy, mgh, right? And we ended with kinetic energy, 1/2 mv squared. So the m didn't matter. So this is 2gh, square root of 2gh is v, correct? So let's figure out what that is. We figured out what h was, so let's plug in. Square root of 2 times 10 times 0.014. It's our velocity. So our velocity is what? Let's figure it out here. 2 times 10 times 0.014, 0.28. So we're taking the square root of 0.28. And I get about 0.53 meters per second. Okay, so now we can take that and plug it in over here. So 0.53, we're going to square that, divide it by L, which is 0.4, plus 0.5 times 10. Overall, the entire thing, we should get about 5.35, and this is tension, so it's newtons. Okay. Describe one modification to double the period of the oscillation. Okay, well, what is the period of the oscillation? 2 pi square root of L over G. Well, there aren't a lot of ways to do this, are there? So if I want the period to double, so effectively I want to double this. So I'm going to say I want this times 2, which means this thing needs to be times 2. But the only thing that here that I can adjust is the length. So how would the length have to change to get a 2 to pop out? Well, the square root of what is 2? Yeah, you got it, 4. So to get twice the period, we would have to get 2 pi 4L over G, correct? So we would have to do 4 times the length, because honestly, you could say something about having gravity, but I mean, or taking a fourth of gravity, but really, can we adjust gravity? No, we cannot. So, be able to let me know that you understand what we're doing and how the length and gravity affect the period and what the relationship is between period and frequency. All right, guys, next time.